So I wanted to do a quick video on the horizon. This is the view from the cockpit of a Robinson R-22 helicopter, which I actually have a license for. This instrument here is the magnetic compass, and it's sighted up this column away from the instrument panel down here, because the instrument panel is full of gyroscopes and electronics. It interferes with the magnetic compass, so they move it up here out the way to eliminate that interference, and in doing so it provides a convenient visual reference for the pilot to use as his attitude indicator, if you like. It enables him to keep the aircraft at a steady attitude, a cruising attitude, and it makes the aircraft more efficient. So he simply uses the stick here, the stick, to align or to lift the nose of the helicopter up or down, to keep this magnetic compass aligned with the horizon, as you can see this guy's doing here. One of the other things that we used to practice was we would hover at any altitude. It could be 1,000 feet or it could be at 10 feet, and we would get this compass on the horizon and we will practice a spot turn, which is using the pedals to turn yourself on the spot, and the idea being you do it perfectly straight and level, and the way you do it is to keep this compass on the horizon at all times, and if you feel yourself deviating from the horizon, you compensate either with the cyclic stick or the pedals or whatever, or even the collective lever. The horizon was always completely flat. We relied on it being completely flat to be able to perform the manoeuvre straight and level. I never saw any indication that the horizon was curved in any way, as that would have hindered this manoeuvre. Anyway, on to AutoCAD. This software is extremely powerful and it's extremely accurate. One thing to note is that if you draw a circle in AutoCAD, it renders it as a series of continually rotating straight lines until you do a regen. And the reason it does this is so that it can, the graphics card can display the image quicker without having to do things perfect. But to overcome that, all you need to do is type REA, which stands for Regen All, and it makes the circle perfect again at that particular magnification until you move or pan. I'll explain why that's important later. The other thing to note is that it does all the work for me. It eliminates human error. So if I wanted to draw a line from the quadrant point here, which is the 270-degree position, all I need to do is hover over the circle somewhere and it automatically snaps, look, to the quadrant point there. So if I click there, put my orthographic on, and if I drag the cursor to the left and type 100, it will draw a line 100 miles in the 270-degree direction. Then if I wanted to join this line to the circle tangent, all I need to do is type in the word tan, hover over the circle, and it puts that green symbol there, look, at the tangential point. It eliminates any human error. It's done all the work for me. I haven't had to do any maths. Okay, so if I zoom into the top of the globe, where I've already drawn a line 6 miles vertically upwards from, let's call it, North Pole. If I look over here, look, the length of this is 6 miles. It's telling us it's a line and it's 6 miles long and it's 90 degrees from the horizontal. Incidentally, what I didn't show is if I select the circle itself and display the properties for it, it tells me here, look, it's a circle, it's blue. It tells me the radius, the diameter and the circumference, and as you can see, these figures here are the generally accepted dimensions of the globe. So everything's drawn to scale, perfectly to scale. Let me zoom back in. There's the 6 mile high line. If I zoom into the top of it, I've already imported the model of a Boeing 747 exactly to scale. And I've drawn a line from the passenger window, the red line here, and I've drawn it to the tangent point on the Earth. Now, you remember I said earlier that that AutoCAD won't render a circle, it'll do it as a series of straight lines. It's done it here, look. So if I type that command REA, it'll bring it to a perfect circle again. And you can see that the line here, which is the line of sight from the passenger on the plane to the horizon, it touches the circle precisely. I then drew a line back from this point horizontally to underneath the aircraft, just here. And you can see that the distance now from the horizon to the aeroplane is 11.99 miles, which is almost double the altitude of the plane above the Earth. And it conveniently actually works as double around this sort of altitude, around the 6 mile high altitude. The distance to the horizon works out to double. If you start going higher and put lines in 100 miles high and do the same exercise, it gets to slightly less than half. For instance, if I did it at 100 miles, it would be what would it be? It'd be about 197 miles, I think, something like that. Anyway, so it seems to conveniently work as double around this sort of altitude. So let's have a look at what this looks like from the perspective of somebody on the plane. So here, again, I've drawn the aircraft exactly to scale. Down here is the height they are above the Earth, 6 miles. So this is directly below them. And then this is the horizon, which is a further 6 miles, giving the total of 12 miles. 12 miles. So let's have a look at the artificial horizon in the aircraft. The passengers on the plane don't experience any nose up or nose down attitude of the plane. The instrument tells them they're flying straight and level. For all intents and purposes they are. However, the horizon is 12 miles below them. What would they need to do in order to correct it? They would need to nose down, but the instrument is reading straight and level. Doesn't work. And this is not what we see. We don't see the horizon 12 miles below us. Let's have a look at the flat Earth model. Same position, just here from the North Pole. This green line here depicts the flat Earth, and I've drawn it at about double the diameter of the globe here. So it's the same aeroplane, same height, 6 miles. This time we've drawn a line out of the window this way, right to the end of the flat Earth, wherever that may be. This is kind of the minimum distance for it, based on the commonly accepted flat Earth models. And we see that the angle from the horizontal, which is the white line here, to the angle that it is to the flat Earth horizon is 0.04 degrees. It's next to nothing. For all intents and purposes, even at the sort of smallest possible flat Earth, the horizon is at eye level. Of course, if this was an infinite plane, then the angle would be approaching zero infinitely. One of the figures I forgot to mention is this: in the globe model, the distance from the aircraft at 6 miles cruising altitude to the horizon is this red line here, which is selected. So if I go over to the properties of it, it's 218 miles. So that's the distance to the horizon at 6 miles altitude, and that gives you an angle from the horizontal of 3.15 degrees. Still doesn't sound a lot, but over 218 miles it gives you almost 12 miles of drop. So let's just quickly wrap this up and have a look at what we actually see. Here's the aeroplane. The passengers on the aeroplane, out of both windows, they see the horizon at eye level. The instrument's reading eye level. The horizon is as it should be. All passengers are experiencing straight and level flight. It all works. Okay, the last thing I wanted to show was what would happen with helicopters if they were to ascend vertically into a hover at various different altitudes. So I've drawn the helicopters here at a massively increased scale. The globe here is still to scale, but I've increased the scale of these helicopters quite significantly so that you can see them. The first one is at 6 miles altitude, then 100 miles, and then 200 miles. And I know that helicopters don't usually fly at that altitude, but the dynamics at play here would be the same regardless. So this is the 6 mile altitude here as viewed by the pilot in the cockpit, and this is the same angle and the same length as in the previous example with the airliner. Now, one thing to note is that the helicopter has been tilted here to align with the horizon here. Now, if you're in a helicopter, the only way to tilt your nose down is to push forward on the stick, on the cyclic stick. But in doing so, it tilts the rotor disc downwards at the front and causes you to move forward. That's how you transition from a hover into forward movement, fast forward flight. You push the stick forward and the nose dips and you start moving forward. There are other things you need to do as well, but that's essentially what happens. So let's see what would happen if we was to ascend to 100 miles. Well, we would, in order to keep the horizon at eye level, we would need to really push the nose of the aircraft down. So this meets the globe at the horizon here. Again, it was drawn in AutoCAD. It is precise, and you can see it forms a 90-degree angle perpendicular to the centre of the circle. And then if we go to 200 miles, it becomes insane. Look at the angle that the helicopter would have to be to keep the horizon at eye level and hover. It just wouldn't work. It can't work. The more and more I look at this globe model, the more and more it goes from being a lie to just ridiculousness, absurdity. I mean, how can you account for this? The way to hover is to keep the horizon at eye level. If I keep the horizon at eye level at this altitude, then we're at all kinds of funny angles. Even at 6 miles high, that attitude, that angle that the helicopter's at there, could only be achieved by pushing the stick forward, which would cause you to move forward into fast forward flight. Just doesn't work. Thanks for watching, folks. Hi there, this is a follow-up to my first horizon video, and in this video I'm going to be discussing these instruments, which you'll find in the cockpit of almost every aircraft in the world. It's the artificial horizon. I'm also going to be talking about this aircraft. This is the iconic Concorde. Unfortunately they don't fly anymore. The last one flew in 2003. Kind of regret not having been a passenger on one of these planes. The reason I've chosen to talk about a Concorde is because of the particularly high altitude that they fly at. They fly up to 11 miles high, and that really presses the point that I'm trying to make in this video with regard to artificial horizons, these instruments. So I'm going to show you a couple of brief videos on how these things work, so stay tuned.
The attitude indicator, AI, also known as gyro horizon or the artificial horizon, or attitude director indicator, ADI, is an instrument used in an aircraft to inform the pilot of the orientation of the aircraft relative to the Earth. It indicates pitch, fore and aft tilt, and bank or roll side-to-side tilt, and is a primary instrument for the flight in instrument meteorological conditions. Attitude indicators also have significant application under Visual Flight Rules, VFR. I like to think of it this way. The centre white line separating the brown or ground from the blue sky is our horizon. The yellow line running across it, think of this as the wings on the aircraft. Now, bearing in mind, if you're looking at the cockpit in the aircraft, you're keeping it in line with the horizon. Now, on this instrument, the wings, or the yellow line running across the horizon, should be in line. If the symbolic aircraft is above the horizon line, the blue background, the aircraft is nose up. If the symbolic aircraft is below the horizon line, the brown background, the aircraft is nose down. Because it is the horizon that moves up and down and turns, while the symbolic aircraft is fixed relative to the rest of the panel, trainees get confused. A standard corrective given by flight instructors is fly the little airplane and not the horizon.
Okay, so I was reading through some of my old textbooks when I was learning to fly. A couple of them here. But this one in particular, The Helicopter Pilot's Manual, Power Plants, Instruments and Hydraulics by Norman Bailey. If we go to the instrument section, we can see this page here is the artificial horizon, and it explains how it works. And the important bits I've underlined there. So let's get a snapshot of that. So it reads, because the horizon bar is connected to the gyro, it remains parallel to the natural horizon. Further down, the artificial horizon gives an immediate indication of even the smallest changes in attitude and has no lead or lag. So what that's saying is that it is an extremely sensitive instrument, and it reacts instantaneously to any attitude change of the aircraft. When the nose is raised above level attitude, the pictorial display shows the same attitude change in miniature. So This is it is mimicking the movements of the aircraft absolutely precisely, and I'm sure any pilot watching will concur that it is an extremely sensitive instrument and does react instantaneously. So let's have a look at one of them opened up and being demonstrated in real time. So this is what the rear of the artificial horizon looks like. This bit is hidden away behind the instrument panel in the aircraft. So this is the front face of it. This here is the gyroscope. It's got a flywheel in there that's rotated at very, very high speed, either electric or air driven. And this is sort of gimbaled inside this mechanism, so it is allowed to rotate freely and independently from the rest of the instrument. So just have a look at it in action. You can see it there, look. It remains parallel to the ground no matter which way you turn it. And it reacts instantaneously, just like the book said. See the quick sudden movement there? And it stayed perfectly parallel to the ground. Okay, let's go back to AutoCAD. Now in my last video, which I suggest you go back and watch if you haven't already, I explained how accurate AutoCAD is. It's used by engineers in all kinds of industries throughout the world, and it is accurate to, I don't know, hundreds, thousandths of a millimetre. And it takes away all the hard work. I don't need to do any maths for this. I can simply draw lines, draw them back onto circles at tangent points, and it will tell me what the angle I've drawn it at is, and tell me lengths of everything. So let's have a look at the Boeing 747 from the previous video, just to recap. It's 6 miles in altitude. If I click this line here, it tells me it's 6 miles high at an angle of 90 degrees from the horizontal. Let me just select the Earth again. I'll just zoom out so you can see it. This is the exact size of the Earth as generally accepted. So if I look here, it tells me, look, it's a circle and it's blue. It tells me the radius is 3959 miles, and it tells me the circumference as well. The plane's obviously been drawn at a much enlarged scale so that you can see it easier. But I've drawn a line from a passenger on the plane from the window. Well, it's actually to the centre of the plane, but it nearly passes through the window there, so it's accurate enough, down to the tangent point on the globe, which is here. So this is the horizon point from the perspective of a passenger on the 747. And from the previous video we showed that it was 3.15 degrees down from the horizontal. Okay, let me just get rid of that and get rid of the 747. Okay, let's look at the Concorde. Now the Concordes can fly up to 11 miles in altitude. So this line here, if I select it, look at the properties, length 11 at an angle of 90 degrees. Now, do you remember the old gyroscopes that you used to have as a kid, and you wrap a piece of string around it and pull the string and it spins up the flywheel? So let's use that as an analogy here, because that's exactly what the artificial horizon is, the instrument that we've just looked at. So imagine the toy that you had as a kid, the gyroscope. This is the axis, and this here, the horizontal, is the flywheel. The artificial horizon in the aircraft is obviously
a lot more accurate than them toy gyros. They remain precisely straight and level with the parallel to the ground. But if you were to take the analogy, this, no matter how high you are with the gyroscope, as long as you're staying above that same point on the Earth, it will remain the same. This is globe Earth we're talking here. It will remain the same. The gyroscope will be, the flywheel will be going horizontal, and the axis of rotation is vertical, no matter where you are up this line here. Okay? That would mean that the flywheel, the horizontal flywheel spinning, is in this plane here, the horizontal. So what is it that the artificial horizon instrument is reading? Have a think about it. It's reading this. It's reading parallel to the ground at the particular point you are above the Earth. Again, assuming it's a globe. Let me just freeze that for a second. Concord flat. And we'll for Concord angle. Okay. I've drawn a line from the 11-mile high point, which is from the pilot's window in the Concorde, and I've drawn that at a tangent to the Earth at the horizon point, just here. So that line there is length 295.3 miles. And if we take a line out from the horizontal here and draw a line down to the horizon point, you can see that it's almost 22 miles. So it's, again, almost double the altitude of the aircraft here, which is 11 miles. And just to clarify that it is the tangential point just here, I've again drawn a line from the tangent point to the centre of the Earth here, which is the precise centre, and it forms a 90-degree angle, so we know that that's the tangent point. Okay, if I use AutoCAD's dimension tool, I can interrogate it and find out what the angle is between here and here, just by clicking the two lines, which I did here. And it turns out it's 4.27 degrees. Now remember earlier when I was reading that section in my textbook about the artificial horizon being extremely sensitive. Now 4.27 degrees is a lot when you're talking about the artificial horizon, and as you can see, the plane, the aircraft is tilted. The passengers on this plane would most definitely be aware that the plane was in a nose down position, without a doubt. And for the avoidance of doubt, let's check out some other official sources of definitions of the artificial horizon. So this is the Free Dictionary. An instrument that indicates the pitching and banking of an aircraft by displaying the movement of a representation of the aircraft in relation to a line representing the horizon. Let's go to this site, which is your dictionary. Artificial horizon, a gyroscopic instrument on an aircraft for indicating the true horizon, and I've highlighted that, true horizon, and the position of the craft with reference to it. If I go back to my textbook that I read from earlier, it says because the horizon bar is connected to the gyro, it remains parallel to the natural horizon. So they're pretty unanimous on it. There's no mixing of words at all. They're saying that the artificial horizon aligns with the true horizon or the natural horizon, which is here. That's what they're saying. But they can't both be correct, can they? It's either the aircraft is tilted down and facing the globe's horizon, or the aircraft is level and the gyroscope, the child's gyroscope analogy works, whereby you've got a 90-degree angle formed here. Based on what I felt when I'm on aeroplanes and when I'm flying in helicopters, that has to go. That is what we feel, that is what we experience. Meaning that the artificial horizon does not point downwards to a horizon point here. It can only point horizontally. And there is only one model where everything we see and everything we observe fits what I've just explained here, and that is the flat Earth model. And one last thing to get your head around is this line here is not the only horizon from the perspective of the pilot. Provided he turns the aircraft round, he can view horizons in all different directions, 360 degrees of horizons, if you like, all the way around him. So what would necessarily make his artificial horizon point specifically in this direction when there's another horizon in this direction? It has nothing to do with movement or forward airspeed. Let's go back to the analogy of a helicopter, and yes, I know helicopters don't fly this high, but let's go to the analogy of a helicopter hovering at this height. He can remain there, straight and level, and we know what the instruments are going to show. But this doesn't necessarily mean that once he transitions from the hover into forward flight, that the artificial horizon is going to suddenly shift and drop to point at the true horizon in the particular direction that he is travelling at. It doesn't work like that. Although all indications and all external sources seem to suggest it should. I hope you've enjoyed this video. It's been quite a heady subject to get my head around. It's led me onto all kinds of other thought tangents, and I plan to make some more videos showing these. So if you like it, please comment, subscribe, more to come. Hi folks, this is part 3. And this is AutoCAD again, and I've drawn these shapes here in 3 dimensions. So we've got a square, a sphere, a circular disc and an irregular shape. So if I just go to the 3D view of them, do a regen. So the sphere here is drawn to the exact size of the Earth. If I click it and click properties, it's telling me the radius is 3959 and the diameter is 7918. So that's in miles. This disc is drawn, the diameter is double the diameter of this sphere, so roughly the size of the commonly believed flat Earth. This square is drawn, the sides are the same as the diameter of the flat Earth, and this is just a sort of random irregular shape drawn to roughly the same size. In the centre of them all, I've drawn a vertical and a horizontal column. This horizontal column is exactly 6 miles from the surface here. So at that intersection there, it's 6 miles in altitude, and I've done that in each one of them, right from the surface, and the sphere from the sort of top polar surface. What I then did is exported these into a program called Autodesk Navisworks. So you can see them here, plan view. One thing to note that I saw straight away is that when I imported them, the program actually renders this sphere by putting a diminishing light around the edges. That sort of gives you a visual representation of a sphere. The disc look is the light is just uniform throughout the whole of the surface. So if I go to Google and just type in moon images, in every image of the moon that you can see, the full moon, the light goes all the way to the edge. There's no diminishing of light on any of these full moons. It's only when it's sort of a half moon or a crescent moon that you can see the actual line of the shadow, and it's a definite line. But all the full moons, they're all uniformly lit all the way around. You see the crescent on that one. It doesn't sort of show that diminishing light as it goes around the surface, around the sides. This program here, if you go to lighting, we've actually got set to headlights, so it's as if we are shining headlights directly on these objects. I can also select scene lights, which puts the light from a sort of different direction. You can see here the light's coming sort of from our top right. Just thought I'd point that out. That's an aside to this video, really. So I can navigate my way very slowly to the centre point where I put them columns. And this is quite laborious, trying to find these columns and align myself with them. So I'll do the first one here, and then for the rest of them I've saved the views so that we can just flick between them easily. Where is it? There it is. If you can see the column just appearing there. Like I said, it's very tricky to get myself aligned with it. I'm inside the square at the minute. Anyway, I have to spend a lot of time aligning myself with the horizon there. So I've saved the views, so I've got square over here. So what we're looking at is if we've dug a hole in the surface of the square, we've climbed down into the hole, and we're looking out at the horizon, sort of dead on our eye level, at ground level if you like. And you can see, because we are inside it and we're at ground level, we can see the sort of underside of the square here and the walls. And you see this underside coming away from you. So what I'm going to do is simulate ascending vertically in a helicopter. I'm going to go to 6 miles again. I know helicopters don't go to 6 miles, but just for viewing purposes, I'm going to assume it can. So let's ascend. There we go. So our eye level now is dead on the horizon, and even though it's a square, it's still very, very flat at this altitude. So let's continue higher, a lot higher. We've gone way, way above the 6 miles now. And as you can see, as we get higher and higher, you can see the square start to appear. And just keep looking down on it, looking down there, and ascend higher. Let's go back a bit, so you can see the square. Let's go to the circle. So this is the disc. And again, we're at eye level. One thing I forgot to mention is that the horizon line, the only way to depict where eye level is really, from our perspective as we're looking at this, is this arrow here, which is a tool in this program. You can see the horizon sort of crosses the center point of that arrow there. So that is how we know we're at eye level. When the horizon is, sorry, when the horizontal bar, the red horizontal bar is in line with this arrow, we know that we're at eye level. So let's ascend on the circle, on the disc. So we're up to 6 miles. I've got to do this slowly, otherwise it goes zooming past. There. So again, the red line there crosses this arrow about halfway down. And already, don't know if you can see that, you probably can't very well, it's already started to form a curve. And that's right, a curve on the flat Earth. Who'd have thought it? Let's keep ascending, and as we ascend further, the curve, as you can see on the here, look, the curve is the horizon is dropping at the edges. Keep moving up, up and up and up, and eventually, if we go high enough and far enough back again, obviously we see a curve. The point I'm trying to make here is that even on a flat Earth, the horizon will appear to be curved. It has to. At some point it has to, if you get high enough, because it is actually a curve. So if you're looking down on it, logically you will see a curve sooner or later. Let's quickly go to the irregular. Again, the horizon is crossing this arrow, or our eye level, sorry, is crossing this arrow. Let's ascend. We just might as well go straight up now. Yeah. So even the irregular shape starts flattening out. We're not even down to the 6 miles yet. You'll see when we do, when the red line, or when the horizon sort of crosses this, and we're dead on eye level. There, oops, just too far there. Let's go to the sphere. Okay, I had to draw the column down into the sphere because to try and align myself with the horizon here was very difficult. It was different to all the other shapes. Just trust me, it was. So let's ascend. Before we do, the horizon's looking very flat. So let's ascend up to 6 miles, and we need to put the bar in the centre of this arrow. So now we're at eye level. This bar is at eye level at 6 miles, and you can see, as my previous videos show, the horizon is below eye level. So this, from here down to the horizon at this point, would be the 3.15 degrees from my previous videos. So let's keep ascending. Just to complete the video. Come back a bit. So the only other possibility that we've not looked at is the infinite plane, but unfortunately on this software I can't simulate the infinite plane. I have to give objects physical constraints or dimensions, and since infinity would be infinity, it won't let me do it. But suffice to say, in my opinion, what would happen on the infinite plane would be that no matter how high you ascended, the horizon would remain at eye level indefinitely. So I hope you've enjoyed this video. It's just to show perspective really, nothing groundbreaking. We obviously can't do these sorts of things in real life, so I guess we rely on computer programs like this to give us an idea of what things would look like. I know it may not be 100% accurate, but I don't know. Interesting nonetheless. More videos still to come. I'm going to dwell on the light on the moon issue a bit more, amongst other things. So if you're interested, please subscribe.
There was a documentary just put out yesterday,
Yep.
a good one by the way, people should check out, called Flatten the Curve, by a bunch of pilots and military people. You know, that's our term. That's our flat earth term.